going to look at how to estimate the difference between two proportions. Okay, let's do a little story, sort of a background to this. Imagine that we were comparing Scotland as a population to United States of America. And we asked people in Scotland, or let's say we're interested in finding out what proportion or percentage of Scottish people have ever been to France. And so the P that we're looking for is a proportion of been to France. And since this is Scotland, we'll call them population 1, and I'll call that number P1. In America, you're going to be population 2, and we are going to find out the same thing. What proportion of Americans have been to France? Now, what I could calculate is an estimate for the Scottish and an estimate for the Americans, totally separate. But what we're really interested in is we want to find an estimate for the difference between the two. And that's where the fun starts, the estimate between of the difference between them. So what we would do is that we'd get a sample. And the sample will be called that guy, which we will read out loud as P hat. And how did that sample come about? Well, we asked 1,000 Scottish people, Scottish adults, have you ever been to France? And 750 of them said yes. And if you think that's quite large, it's not that wrong. Me and my wife, we went back home quite a few times to Scotland. And one of the things we did is we got a plane from Glasgow Airport, and I arrived in Paris 1.5 hours later. So it's an hour and a half, I think it was an hour and a half anyway, 90 minutes to Paris. So you can see that for an American to go to France or Paris, it's a big heavy duty flight, right? It's a lot of money and it's a lot of time. But you could quite easily from Scotland fly to France, spend the whole day there and fly back home. And it wouldn't be that onerous. I had a niece, for instance, who loves traveling, and she did, I think she did a day to Germany, Berlin. She flew over to Germany for the Christmas market, and her and her boyfriend flew over early, spent the whole day there, flew back at night. Wasn't that strange. So 750. Now, N1 is the size of population 1, which is that guy. Right, let's do sample 2. It's going to be called P hat 2. And this time, for whatever reason, we asked 2,000 Americans, have you ever been to France? And I'm exaggerating. I'm saying 1,400, which is probably not accurate, but I'm pretending it is. And in this story, the sample size is 2,000. Now, these two guys get turned into decimals. So that's 0.75. And this guy here is 0.7. So superficially, would you agree it looks like more Scottish people have been to France than Americans? Right. It's about 75% compared to 70. Now, the question really boils down to, is that difference significant or not? Why do I say it that way? Do you know if I did another sample of 1,000, couldn't I have got 630 who had been to France? Couldn't I do another sample of Americans and maybe I got 72% the next time? So won't these samples vary? And so will these. So what we're wanting to do is we want to compare the two, and that's what the difference between two proportions does. Now there's another guy that we need to get the number for. It's called Q1 hat. Q1 hat is 1 take away P1 hat. It's basically the people who said no. Right? In these stories, there's the yeses and the nos, right? So if yeses is 75%, then the no is 25%. And if I do the Q2 hat, one minus P2 hat, Q2 hat ends up being 0.3. And we are going to find a confidence interval. And there is a formula that we use that's going to be the same formula every single time that we do this. So here it goes. P1 hat, take away P2 hat. Plus or minus a magic z-score times a really big ugly calculation. P1 hat, Q1 hat over N1. P2 hat, Q2 hat over N2. This big ugly square root is basically the standard error of the sampling distribution. Now, there's one guy that I haven't been too specific about. Do you remember the magic z-scores? Right, the magic z-score for 90, for 95, all those guys. That's who ZC is. To remind you who those guys are, there they are. Okay, for my story here, what do you want? An 80? I don't like 80. What do you want? A 90, a 95, or a 99%? What kind of confidence interval do you want me to calculate? Pick one for me.
$95.
Okay, sounds like a plan. 95 look good. Can you read? I'm trying to move my camera a little bit. Can you read the top line now that I've moved it a little bit higher? Is there anything missing? Looks good, okay. So we're going to do a 95% confidence interval. I think that's what Chris said. So P1 hat is 0.75. Take away the American P, which is 0.7. I'll just put a little bracket around that to emphasize it. Plus or minus. The magic z-score for 95% is 1.96. Now it gets messy. P1 hat is 0.75 and the Q version of that is 0.25. And that gets divided by how many Scotsmen were asked, which is 1,000. You then add to that Q2, which is 0.7, 0.3, and there were 2,000 Americans. Now, you know that's going to be a really messy calculation. And so you won't really be able to use salt in any useful way here. What we're going to do is the old-fashioned way of doing things. Right, this guy, take away this guy, is positive 0.05. Give or take. Okay, I'm now going to multiply this mess together. 1.96 times square root. 0.75 times 0.25 divided by the 1,000 Scotsmen that you asked. plus 0.7 times 0.3 divided by the 2,000 Americans that you asked. Oh, so the answer that we get here is, give or take, 0.03. I'll just make it 2 decimal places. I could have done more accurate. Now, can you remember what this guy's called? The 0.03 guy. He's given a very specific name. Can you remember what he was called? Yes, it's called the margin of error. So I could say that the estimate for the difference between these two groups is 0.05, give or take 0.03. The way it works in the homework is that you tell me what's called the lower limit. You'll then tell me what the upper limit is. So you'll calculate those separately. And you might sometimes be asked to write down the margin of error. Well, I know that margin of error is, right? It's that guy. Now, if you take this and subtract that, you get 0.02. And you take this and add the margin of error, you get 0.08. And that's all well and good, and that is correct. Human beings, however, I don't think that's clear what the heck's going on. So that's basically 2%, and that's basically 8%. So what I am saying here is that I am 95% sure that the difference between Scots and Americans who've been to France is at least 2% up to 8%. In other words, don't Scottish guys go to France more often? And the difference is about 2% more, could be as much as 8% more. Right? When I phrase it that way, does that information sound a little bit more understandable? Right? That the 95% confidence interval for the difference is somewhere between 2 and 8. So far, so good. Right. Now, let me tell you what we can say for sure then. Since all these numbers are positive, doesn't that mean that there's evidence that Scots have been to France in greater proportion than Americans? And I have to use the word proportion. I can't say numbers because Scotland's only got 5 million people, right? So there's probably been more Americans been to France, but a smaller percentage of Americans. Does that make sense? 300 million people. If only 1% of you went, that would be 2/3 of Scotland, right? That's how big you are compared to Scotland. Do we get the gist of this question? Right. Now, the good news is that pretty much this process is going to be the same each time. You're going to be given two populations. You're going to be told things like how big the samples were, how many said yes to the question. You're going to calculate the Q guy by just taking that away from 1. And then you're going to do a 90 or a 95 or a 99, whatever they feel like confidence interval. You're going to find a lower limit, you're going to find an upper limit, and then you're going to get a margin of error. Are we good? So I'm going to, in a few moments, I'm going to use you lot to do a very small sample. Right. So here are some rules of the game. You cannot do what we've just done. Unless those guys are bigger than 5. What does that mean in English? At least 5%, 5 people have to say yes, and at least five people have to say no. So you can't use this math that we've done. If you ask 2,000 people a question and only 4 of them said yes. So can you imagine you had a sample of 2,000 people and you went and said to them, how many of you have ever been to Mongolia? And 4 of them said, yeah, actually I have. Well, NP would only be 4 in that case, and that is definitely not enough. Does that happen very often? Not really. Do you know the only time that's realistically going to happen is probably when you only have a tiny sample. Can you imagine you only ask 20 people something? Couldn't you get quite a few situations where less than 5 said yes? Are we cool with that? Right. That's basically the major rule. So let's do a sample. I have 1, 2, 3, 4, 5, 6. We have 6 people. And so I'm going to have 2 populations. One of them are going to be people who live in America, and the other one is going to be a pretend country. Right. So 1, 2, 3, 4. I'm going to have to break all my rules just so that we can do this. So Logan, you may not know this, but you are representing 10 people. Right? And so all of you are going to represent 10 people. And I'm going to ask you the question. Let's see what we could ask you. I need at least one person to say, oh, well, I'm here. I can always make sure it's yes. Okay. Have you been to Europe? So this is on all 5 of you, including me, I guess. So all 4 of you that are left. 1, 2, 3, 4, 5. All 5 that are left. How many have been to Europe? It doesn't matter if you were in the military and you just dropped off at Germany on the way home or whatever. It still counts. How many have been to Europe? I'm glad I am here because I have. That means, since I am representing 10 people, that was a sample of 60. And the number of people who said yes were 10 out of 60. You really have to go to Europe. It's a cool place. And that ends up being 0.17 because I'm doing things to decimal places. What's the value of Q1 hat? P1 hat is 0.17. What's the value of Q1 hat?
.83.
Yep, take away from 1. Or if you forget the decimal point, don't they always add up to 100 in this case? Now, I need a pretend country. In this pretend country, we asked 200 people. And the number that it said they'd been to Europe was 40, which is 0.2. So that'll be Q2 actually. And Q hat 2 then, now let's test this out. What would Q hat 2 be for the second population?
80.
Yeah. 0.8. Okay, so we've got the information that we need, right? These are the numbers you need in every question. You're pretty much going to be told them, but we've calculated them as well. So I need to know how big you want my confidence to be. Do you want to do a 99? Do you want to do a 90, 95? I don't like 80, so I'm not picking that. But who do you want this time? Just pick one.
99.
Thank you. So we'll do a 99% confidence interval. So it's going to be P1 hat, take away P2 hat, plus or minus, the magic number for 99 is 2.58. And then the weirds P1, Q1 over N1, P hat 2, Q hat 2 over N2. Right, P1 hat was 17. P2 hat is 0.2. 2.58. So that guy is 0.17 multiplied by 0.83 over 60. And the other one is going to be 0.2, 0.8 over 200. Well, that take away that is a negative number, and you will get negative numbers in these questions. So don't let that distract you. So time to do this fella. 2.58 times the square root of 0.17 times 0.83 divided by 60 plus 0.2 times 0.8 divided by 200. And the answer I get here is 0.14. Now, as a percentage, the margin of error here is huge. Can you think of any practical reasons why that margin of error is so big?
Because we have such a high confidence interval?
That's definitely true. Good answer. Can you give me another reason? Because that's correct, that is the right reason. But is there another reason why it's so high? Especially this one. Aren't the samples quite small? A typical sample that you would get from a company like Gallup poll is typically about 1,000 and change. They normally do like 1,010, 1,024, that kind of number. So that also contributed. You put both of those together and they kind of double up on each other and it becomes even worse. What's that going to look like? Well, if I do the lower limit, that take away that subtract that is negative 0.17. If I calculate the upper limit, it's a positive number. Me personally, I like decimals to be turned into percentages. We are saying that the difference between the America and this pretend country is somewhere between negative 17% all the way up to positive 11. Now, on this side, it means that the first one's less than the second, right? Less Americans go than the pretend country. On this side, doesn't it, because it's positive, mean that more do? So in this case, there is no evidence that one is bigger than the other. Now, I can tell you what our interval says. It says that the difference between these could be negative 17. That means the Americans have been to Europe 17% less than the pretend country. It could be 11.11, positive 11. In that case, it's 11% more than the pretend country. So in a lot of ways, we don't really know what the difference is, do we? It could be bigger, could be less, you know, we don't really know. So let me show you the three permutations. I'll use decimals because that's the ones you're most likely to work with. There's one interval. There's the second one. There's the third one. So imagine these were your confidence intervals. If they are all negative, the first thing is less than the second thing, right? The first population, whatever it is less than the second. If they're all positive, the first is greater than the second. And if there's some positive and some negative, as we have here, you don't know. Right? By that I mean you don't know if one of them's bigger or less than the other one. Do we have any questions on that, or are we good so far? Okay, Bailey, thank you for the thumbs up. Let's move on. Oh, thank you, Valerie. So let's see where else we're off to. I am now going to look at some homework questions. Just make it a little bit bigger. Not quite sure what screen you're looking at, so that's weird. Okay. Too much, darn it. Okay, here we go. So here's our first question, question 5. Oh, I got the answers. That's fine. Let's show you where the answers come from. For this problem, carry at least 4 digits after the decimal in your calculation. So they're saying, look, we want lots of accuracy, at least 4, right? If you can do 5 decimal places, that's probably better, but at least 4. I'm writing down the key information from this question. I'm going to then return to the white screen so you can see what the working looks like, and then we'll come back and see if we got it right. So here we go. In a random sample, hey, am I on the right one? I bet you I'm not. What the heck's going on? There's something not right here. This should be 7, 3, and it should be difference in 2 proportions. But it's not. This is a difference in 1 proportions. What on earth happened? Well, let me go and do something here. I'm going to go in. I think I know what happened. Right, you know why I talk to myself all the time?
Why?
It's the only way to have an intelligent conversation.
That was a really good one.
Yeah, it took you about 10 seconds to took you 10 seconds to get that one, didn't it, Valerie?
Yeah.
Okay, I think I've gone and screwed up with the naming of some of these questions. I think that's what I've done. Okay, we got them. All right, I found them now. Okay, we are cooking. So let's go back to one of these questions. Right. I've now found a question that is the difference between 2, which is what I was hoping for. Here we go. So in this question 11, a random sample of 300 unmarried couples found that 280 had 2 or more personality preferences. So population 1 is people that have a lot in common. And in this population, they asked 390 people, right? And they found 280 of them had a lot in common. And then in the second group, 580, they were married as well, a different sample, married couple, with nothing in common. And out of a sample of, what, 580, they got only 32 were like that. And we're being asked to find a 90% confidence interval. Right? So all the numbers were there, they were in the story. Let's show you what the numbers look like. I get two populations. One is people who have a lot in common. The other population are people who don't have a lot in common. And we are going to find a 90% confidence interval based on that. So there were 390 people, 280 out of 390 have a lot in common. Do a quick calculation because I need decimals. 280 divided by 390 comes out to be 0.7179. So I'm doing that to 4 decimal places. In the other group, P2 hat, it was only 32 of them out of 580. And that comes out to be 0.5517. Okay. Now, if you want to do a 90% confidence interval, it's going to be P1 hat take away P2 hat, plus or minus. Oh, my magic Z score, almost forgot about that. 1 point, put a big bracket around it, 1.645 square root P1 hat, Q1 hat over N1. The same thing with 2, right? Oh, I forgot one of the numbers I'll need. If that's Q1, P1, won't you get Q1 by just subtracting that from 1? If it's really got a lot of decimals, you're probably safer doing it on the calculator. So 1 take away 0.7179. And the answer I got is 0.2821. And if you go to this guy and you go 1 take away its value, you're looking at 0.4483. P1 is 0.2821, take away 0.4483. Are we good so far? Plus or minus 1.645. I'm not even sure I want to write you these numbers. Can I just point and say, that guy's going to be him, that guy's going to be him, and that guy's going to be him, and just pretend I've written them? Because I'm not sure what the benefit is to writing all those decimals, because won't it be done in a calculator any moment now anyway? So if you take 0.2821 and you subtract 0.4483 from it, you get negative 0.1662. Give or take, here's the calculation coming up. 1.645 times a square root. It's going to be that guy divided by him. So 7179 times 0.2821 divided by 390. Add that guy times that guy divided by him. So it's going to be a 0.5517 times a 0.4483 divided by 580. And I get 0.050, just rounds up, 6. Are we good so far? Right, so I got an upper and I got a lower. What am I going to do here? This guy, take that guy away, so I guess I should do that in the calculator. 0.1662, take away 0.0506. That doesn't look right. It's a negative number, that's why. So it's negative. Now let me show you that on the calculator. That's a negative. This is a subtract. They look very similar, but it's not the same thing. So I'm hitting the negative button. 0.1662. And then I'm going to hit the subtract, that weird decimal. And I have negative 0.2168. And what's the other guy going to be? That one, add that guy. So negative 0.1662. Oh, yeah. If I had a brain, I'd be dangerous. Does anybody know the mistake I made? Because I do.
You put the z-scores, or sorry, the q hat where p hat was supposed to be.
That could be a mistake, but that won't matter too much because because you're multiplying them, it doesn't really matter which order, but that could be a mistake. No, it's this guy here. I said he's 0.5517. He's definitely not that number. There's a 0 in there, isn't there? So it's 0.0557. And that pretty much means that that this number is wrong and this number is wrong, and I don't know if it's recoverable. It's probably better just starting again with a new question. But if I was to fix this question, wouldn't this now have to turn into 0.0557, which means that this would turn into a new number? And wouldn't I get these guys with new values for both the P and the Q? And that would mean this would be a new number and everything else. Okay, I screwed that one up. I will be extra careful with the next one. So let's pick a different story. And the one I'm going to pick is question 15. And I'll just write it and read it. I think maybe that transfer was too much for my poor brain. This one is a clinical trial. You're going to have two groups. There's going to be an experimental group. They're going to get the new treatment. Does anybody know what the second group's called in a clinical trial? Experimental group, what do you call this, the other people?
Is it a control group?
Control.
Yeah, that's the word. So they get the old treatment. Sometimes the control group get a placebo, right? But since these people have got burns, I don't think it's a good idea not to treat them, right? So they get treated with, you know, whatever the cream of the day is, right? Whatever they used to treat. They're not bad burns, right? They're not, you know, third-degree burns, but they are burns. And this new treatment is called a plasma compress treatment. Not that you need to know it for the question, but it's nice to know anyway. It's a plasma compress treatment. Now, from what I know of compresses, and I hope this is the same word in America as it is in Britain, isn't a compress like a pad that you place over something, maybe tighten it down, cover the burn? Is that what a compress means to you? Yes, no, maybe? Got it, okay. So can you imagine they've got this new plasma compress treatment, right? So you come in with a burn, maybe you were doing some cooking and hot water got on your hand, and right, you get some burns, and they put it on. And they decide what success means, right? Now, in some cases, success is the patient living. But in this case, success is, did they have any scars left after they were healed? Right. So if it's not that bad a burn, you might be able to do that. So what happened in this control group was that they had 334 patients that were treated, and 251 of them, right? 254 actually had no scars at the end. So I'm going to be really careful. 254 divided by 334. And it was, I would call that a pretty good success rate. I'm just going to work to 2 decimal places. Well, okay, I'll work to 3 because the question said 3. So it's 0.76, yeah, 0. Now that makes Q1 heart 0.760 gets you 2, 3, no, it gets you 240. 240. Now, what about the control group? Well, according to the story here, there was 422 patients in that group. And of those, 105 had no scars at the end of the treatment, which definitely doesn't look anywhere near as good as the new one. So 105 divided by 422, again, try to be careful, 0.249 to 3 decimal places. And that makes Q2 heart 0.751, which I just did in my head. Are you comfortable that in a story you'd be able to read where these numbers are and know what they are, right? Superficially then, about 76% success rate, about 25% success rate. Isn't this new treatment roughly 3 times better? But if we wanted to prove that it was better, what we need to do is we need to find a confidence interval for the difference between them. And we want to show that that confidence interval is full of nothing but positive big numbers, right? Because that means positive numbers means the first guy is bigger than the second. In this story, it's a 99% confidence interval, is it? Yeah. So a 99% confidence interval. P1 heart, take away P2 heart. For a 99, the magic number is 2.58. The square root of P1 heart, Q1 heart over N, P2 heart, Q2 heart over N2. So I've got 0.760, take away 0.249, put a little bracket around that, plus or minus 2.58, the square root of this guy times this guy divided by that. Maybe I can squeeze that in. 0.760 multiplied by 0.240 divided by 334 plus 0.249 times 0.751 all over 422. Let me pause there. As far as you can tell, does it look like I've done everything correct? You don't see anything that's wrong or switched places or anything obvious? We call this guy good? Right. This guy, take away that guy. Taking no chances, I'll do it in the calculator. 0.76 subtract 0.249, and I'm looking at 0.511 plus or minus whatever this looks like. So here it goes. 2.58 times a square root of 0.76 times 0.24 divided by 334 plus 0.249 times 0.751 divided by 422. Fingers crossed. We get, give or take, 0.081. Everything's to 3 decimal places, right? That seems reasonable. I'm not saying it's perfect, but it seems reasonable. So we're going to get a lower limit. We're going to get an upper limit. And we'll see what that looks like. If you take that and subtract that, so here goes, 0.551, take away 0.081. I get 0.47. And if I go 0.511 and I add 0.081, I get 0.592. And I made a mistake, but I found it. That guy there is actually 4.3. Now, the answer that they have in the WebAssign are these two numbers. What went wrong? Why am I just a tiny bit out? Any ideas? Why I'm a little bit out? It's not that I've done any mistakes in my calculations. I fixed the only mistake, which is that one. I've been rounding off every single place here to 3 decimal places. If you do a lot of calculations and you round them off to 3, do you know that where your final answer can be a little bit out? So the moral of that story is, work to 4 decimal places. So even if the question says, I want the answer to 3, do all your working to 4 decimal places. And then only when you're about to write the final answer, do you then round it off to the 3 that they want. And that's basically just to take care of cumulative errors. Now, I could do 5 of these questions the same way, and 4 of them would be fine, right? 4 of them would just work out the exact same numbers. But 1 out of the 5 could easily be a little bit out. Now, if you look about it, would you agree it's tiny? It's just the last digit is 1 round. one out. But you know what web of sign is like? If it ain't the number, it's wrong, even if it's everything except the last digit. So just to save yourself a whole load of grief of getting frustrated, well, you try and remember that if they say, I want the answer to 2 decimal places, that you'll work to 3. And if they want 5, well, God, I hope they never do, but if they wanted 5 decimal places, can't we just work to 6 and then round off at the end? So I'm much happier about that answer than I was the previous one. Oh, while we're still on this, I haven't finished. If I convert this into percentages, and I'm just going to use the numbers I've got because they're pretty similar. Would you agree that these numbers are all positive? Right? So the difference between the 2 treatments is a positive number. Does it not make treatment 1, the plasma, more successful than the old treatment? So that would be put up in a medical journal, probably one to do with burns. You know, they've got medical journals of, you know, any specialty. I bet you if you were into the medical field, or if you were in a ward that just specialised in one thing, you might find out that the doctors there who specialise in that would have articles written and read from the Burns, I'll call it the American Burn Society, right? And they produce this. Now that hits the medical community, and they look at this data and they say, whoa, yeah. When we get people who come in now with mild burns, instead of using the cream that we use right now or whatever treatment they're using, you know, put cream and bandage it up and clean it from time to time, we're going to buy these things and use them. And the advantage of that isn't that they don't get cured, because both groups would get cured, but won't this one prevent scarring? And so you know that the person, what was the word I'm looking at? Would you agree you just don't want a scar if you get burnt, right? So it helps the community. And I can imagine if the burns are in really noticeable places. You imagine you get burnt on your face. Would you agree in that situation, you definitely don't want a scar? Now, if you get burnt on your forearm, if there's a scar there, who knows, right? It won't really be too big a deal. So it might be a case of, this is probably going to be more expensive because everything that's new is. Right? Have you ever noticed that when you get a new drug, you know, for whatever your ailment is, it costs an absolute fortune, and then it goes generic, whatever it is, 10 years later, and it's like 50 cents a bottle, right? But when you were buying it the first time round, it was $50 a bottle, you know, that kind of thing. And these things here will cost a fortune, right? The pharmaceutical company is going to charge that because they get oh God, I wish I knew. Does anybody know how long you get if you have a new pill, a new pharmaceutical? How long does the company get to be the only people who have a monopoly on it and therefore get to charge a lot? Is it a 5-year before it goes generic, or is it longer? Let's make it up. In 5 years, it's cost a fortune. But in year 6, don't you get the generic version and it's a much cheaper treatment? I think that one went pretty good, didn't it? Little hiccup, but pretty good. Let's look at we're going to do an entire story about ducks, but I'm going to change it because I don't want to use up this question because it's such a good question. So, because I'm into Scottish things today, we're going to have 2 populations. Scottish duck, whoops. And we won't pick in the Americans this time. English duck. And we are interested in the hatching ratio. That basically means, I know they lay an egg, but not all eggs end up being baby ducks, right? They don't all hatch out right. Right. So we want to know whether Scottish ducks are better or worse than English ducks as far as the hatching ratio goes. So we collected some data. In the Scottish duck, we collected 200 eggs. And of those 200 eggs, 137 of them actually hatched. And we got 300 English duck eggs. And we found out that in that case, 160 hatched. And I'm doing all my calculations to 2 decimal places, just so that we can get through the process without spending forever worrying about 6 decimals. So let's find out what the success rate is. Well, 137 out of 200 hatched. So in this case, you get about 68.5% success rate. And in the other case, you get about 53% success rate. Q1 hat is 0.315. And Q2 hat is 0.467. So far, so good. So we are going to do 3 questions, which will pretty much take us to the end of today. We are going to find a confidence interval, a 95% confidence interval, just for Scottish ducks. And then we're going to do a 95% confidence interval for English ducks. And then to finish, a 95% confidence interval for the difference. Right? So going to be a lot of things going on. So let's do the Scots ones first. And if you want to find a 95% only using the information from the Scottish ducks, it's going to be P1 hat plus or minus the magic Z score for 95 times P1 Q1 over N1. Do you see that's like half the formula that we used when it was a difference? Great. Now what does that look like? 0.685, give or take. Oh, let's test you. Anybody know what the magic Z score for 95% is? Anybody remember? 90. Thank you. Correct. P1 is this guy. Q1 is this guy. And it's divided by 200. So it's 0.685, give or take, whatever that is. So 1.96 times square root 0.685 times 0.315 divided by 200. And I am looking at 0.064. And so I'm going to have a lower limit and an upper limit and a margin of error. Well, I know the margin of error is 0.064. Take that away from that. Let's see what you get. 0.685. Take away 0.064. and you get 0.621. And if you add those guys together, you get 0.749. And for me, that means that for Scottish ducks, somewhere between 62 and 75% of all their eggs will hatch into baby ducklings. Now we're going to go through that same process now with the English ducks. So I'll just move this over here. Let's see what the English looks like. Well, a 95% confidence interval is going to be p hat 2, same magic score, a PQ thing over at the end. So that's going to be 533 plus or minus 1.96 times the square root of that guy times that guy divided by that guy. So 0.533 times 0.467, and that's going to be divided by 300. So it's 0.533, and then I'll go through this horrible mess. 1.96 times the square root in this case it's 0.0. You know, I've been saying 2 decimal places, but I've really been doing it to 3, so let's pretend I meant 3 all the way through. So 0.056. And that's going to give me a lower limit, it's going to give me an upper limit, and it's going to give me a margin of error. And if you take 0.533 and you subtract 0.056, you get 0.477. And if you take the number 0.533 and you add that guy, you get an upper of 0.589. And for me then, 47.7% all the way up to 58.9%. So roughly, very roughly, if you use English ducks, you'll get 48 to 59% will hatch. Now, why could that be important? Well, you know, if you are in duck farming, that's what you call it, don't you want to use ducks that when they lay eggs, most of them can be hatched and turn into baby eggs, right? Or baby ducklings, because you're selling ducks, right? That makes sense? So you might want to know that. So the last piece of the puzzle is we're now going to find a 95% confidence interval for the difference. Okay. If you look at the range of the Scottish and the English ducks, it's quite hard because you've got 2 different intervals to somehow merge them together and come up with a good idea for what this could be. Because couldn't the real answer be a little bit on the high side? And here, couldn't the real answer be a little bit on the low side? Or it could be vice versa. So how do we put it together? Well, that's what this is for, right? It's that one, give or take, 95. That guy. Have you noticed it has a very similar look? You see one guy, a difference. one guy, two of them. Now let's see what we get. P1 hat, 0.685. Take away 0.533. Give or take 1.96. And then this horrible mess. Okay, I guess I'm committed to doing it now. 0.685, a 0.315, and 200 Scottish ducks. And the other one is 0.533, 0.467, and that's over 300. So 0.685 take away 0.533 gives me 0.152. Give or take this mess. A bit higher up, I think. There, that's fair. 1.96 times the square root of a really ugly calculation. That's the Scottish bit done. And 467. Hope I didn't do anything wrong. And I get 0.08 round off to be 6. So I'm going to have a lower limit, going to have an upper limit, and a margin of error. And the margin of error is this guy. Right, take them away and see what we get. 0.152, take away 0.086, and I am looking at a 0.066. And then if you take the two but add them, you get 0.238. And I would convert these to percentages. So the difference between the two is completely positive numbers. That tells me Scottish ducks have a higher hatch rate than English ducks. How much higher? Yeah, at least 6% higher, right? Now that's at the low estimate side. Couldn't it be as much as 23, 24% higher? But whatever is going on there, wouldn't you still choose a Scottish duck if you were into duck farming? Right, because you want to increase how many ducks you've got. You want a good hatching rate.